So not necessarily the common coin, but the common coin is kind of the most standard way. Well, basically we need some randomness because there is so-called FLP impossibility that basically states that it's impossible to have a consensus algorithm that is asynchronous and deterministic. So the source of indeterminism that most asynchronous algorithms use is a common coin. And the common coin is basically a common coin is a device that allows independent parties to generate the same sequence of random bits. And the main properties that one usually expects from a common coin is that it is unpredictable. So basically you cannot know in advance what the result will be, only when you flip it. And it should be uncontrollable, so you cannot influence the result of the next flip. And how this is usually achieved in practice is by using, as Pierre already mentioned earlier, by using threshold cryptography, threshold signatures, things like that. It's quite complex, quite complex things, and it usually requires some synchrony or something. So basically, this is something we didn't want to use because of our requirement for simplicity and because of our requirement for being permissionless and asynchronous. So we actually, in PARSEC, we do not use common coin. We substituted it with something called a concrete coin, but Pierre will talk about that in the future. And right now, I will walk you through the rest of the process of achieving consensus with the assumption that we are actually using a common coin. The substitution is pretty trivial, but it's just easier to see if we assume that we have a common coin that basically causes a bit to magically appear in the sky, and everybody sees this single bit and can agree that, okay, this should be the next random bit. So let's come back to this gossip graph. This time we again reset everything. So this time A0, B0, C0, D0 are those events with auxiliary values from before. And now we want to reach a decision. So what we are now going to do is, well, if we see a supermajority, well, first we need to see a supermajority of auxiliary values from different nodes. Why? Basically, well, you will see why in a moment. But what this means, well, we can have three cases there. We can have a supermajority that agrees for true, we can have a supermajority that agrees for false, and we can have no agreeing supermajority. Oh, and important thing, we only count towards this supermajority the auxiliary values that we already have in our bin values from before. So these bin values that we kind of established earlier now also act as a filter for auxiliary values. So, for example, Bob and Carol only have true in bin values, so they will never count the auxiliary values of false from Alice. They will just ignore it.
That would be true at B0, but subsequently the bin value goes.
Well, yeah, it might propagate, and then yeah, that's true. Okay. So basically, what happens now is once we get to an event that sees a supermajority. Okay, so let's maybe go further. So A1 actually already sees a supermajority of auxiliary values because it sees A0, B0, and C0. And since Alice has both values in bin values, both true and false, she accepts both false from Alice and two truths from Bob and Carol, which means there is no agreeing supermajority. So in such a case, she resets the consensus protocol. She starts a new round of consensus. But she takes the coin value, actually, as the next estimate. So in this case, we assume the common coin returns false. So false will be the next first estimate for Alice, because she saw no supermajority. In the case where we see an agreeing supermajority, which actually happens in B2, because B2 sees well, B0, C0, and D0, in this case, well, if the agreeing supermajority also agrees with the coin, we decide. We just say, okay, this is the end, we decided on this value. If it doesn't agree, we take this value of this supermajority as the next estimate. So since in this case the coin value is false, we cannot decide because the agreeing supermajority is for true. So we will restart the consensus algorithm, but this time taking true as the next estimate. So this is what Bob will do at this event. So a similar thing happens to Carol, because as before, she sees B0, C0, D0. This is a supermajority for true. So true is not agreeing with the coin. Bam, it goes to next estimate, and the same happens for Dave. And what if the common coin value was true? Well, if it was true, then Alice would estimate true. She is in the same situation. Basically, she sees true, true, false, no supermajority that would agree, so the next estimate is the coin value. But Bob, Carol, and Dave can all decide, because they see a supermajority of true values. Common coin is true, so now they say, okay, finally everything agrees, we decide. And bam, approved. Okay, and basically what, maybe let me return to this slide. Well, Alice still hasn't decided, but it's, we actually have a solid proof that if a decision has been made, then everybody will eventually make the same decision. So basically Alice will be forced to run another round, possibly another few rounds of the consensus protocol, this time taking those decisions from other nodes as the estimates for the next round. But it is guaranteed that eventually she will reach the same decision as those events from Bob, Carol, and Dave. So everybody will eventually decide true in such a case. And let me also remind that this is just a result. This agreement about true is just an agreement about Alice, which basically means everybody now agrees that we will consider the interesting event created by Alice to be the next event that we agree in the order. But there are 3 other meta-elections that can also reach true or false, which consider Bob, Carol, and Dave, but we won't illustrate them here. Yeah. And once we have all those results of meta-elections, once we collect a result for every member of the network, then we can take the oldest interesting events created by the nodes that we decided true about. So basically we consider the oldest interesting events from those nodes. And we count if there is some interesting event that has a majority, that basically occurs the largest number of times. If there is such an event, we just take it as the next agreed event in the order, because basically, apparently everybody wants this to be the next event. So why are we to disagree, right? If there is no such event, or if there is a tie, for example, 2 nodes wanted one event and 2 nodes wanted another event, and we decided that we should consider all of those propositions, then we need some kind of a tiebreaker. And this is actually a detail. Well, we would like this tiebreaker to be as unpredictable as possible, because this basically gives the nice property that it's harder to influence what will be the next approved event. Otherwise, you could try to force ties and then generate events that would go higher in the order. But basically, one idea we came up with is to take hashes of the interesting events that are being considered for the next place, concatenate them in some predefined order, like, I don't know, lexicographic or sort by value, because those are hashes are just numbers, right? We can concatenate those, hash the result, and then, for example, consider XOR distance from this result of the hashes of the events. So this is pretty random, because hashes are quite random. And basically, we wouldn't be able even to predict which event will come out on top before knowing which events are even considered, because this influences the end result of the hash. And just like that, basically, we pass from binary consensus to full consensus about the next event. So this way, using the building blocks from literature, we get problem solved in PARSEC. But this was with the assumption that we have a common coin, and we actually use the concrete coin. So I'll let Pierre describe a bit what is the difference.